only talk, the only online talk. It's from Daniel Brandenburg. He was supposed to be here, but unfortunately had last-minute issues. So since the experiment he's working on is so important to us, we invited him to give an online talk, and he accepted our invitation. So thank you very much, Daniel. Okay, so we can start. Thank you.
Thank you. You hear me okay?
Yes.
Good. Okay, so yeah, thank you so much to Anna and to the other organizers. I really am disappointed I can't be in person, but I really appreciate the honor of still being allowed to present for you today. So I wanted to show kind of a selection of things that we've been working on and try to talk to you about what I think we've accomplished over the last few years and a few things that I'm excited about that are coming up. So my talk is called Photon-Mediated Processes at STAR, and the focus of it is studying the electromagnetic fields of heavy ion collisions. And here on my title page, I have a list of papers, either STAR experimental papers or quite a few phenomenology papers that I and some of my co-authors have worked on. So most of what's in this talk will be coming from these papers. And then I'll talk about some of the new things that we're also working on. So I think one of the motivations actually when I started my postdoc at Brookhaven National Lab a few years ago was that there was quite some interest in the effects of electromagnetic fields in strongly interacting matter. And there's quite a few different ways that those strong electromagnetic fields can manifest. But one that's been quite important in our field over the last several years is the chiral magnetic effect. And it's been especially in the spotlight at RIC because of the isobar run that was carried out in 2018. And this was a huge investment and a huge amount of work to look for the chiral magnetic effect in a blinded way. So we took collisions of these two different isobars. So they have different charges, but the same total mass. And this was meant to allow us to actually look for differences that are driven by the magnetic field. And what you can see on this slide is a compilation of many different results where, unfortunately, all of them came out below the baseline of the expected signal. And so this was motivation for me when I was in my postdoc to really ask, in a sense, a more fundamental question of how well do we actually understand the electromagnetic fields from an experimental standpoint. So obviously we have very well developed theory being a QED process, but how well do we experimentally actually constrain these fields? And there's different ways that you can ask that question. You can ask it about the X dependence of the fields. One thing that our field is very interested in is the lifetime dependence and whether or not these fields are trapped by a quark gluon plasma. And then there's other important things like, do the fields change significantly on an event-by-event basis due to fluctuations in the structure? So these are the kind of questions that got me motivated. And what I wanted to do was use photon-mediated processes to try to address or at least approach some of these topics. And that set me down the path of the Breit-Wheeler process, which is what I'll start out by talking about. And then really from this Breit-Wheeler process, there's a bunch of different applications that we have developed that allow us to investigate in different ways the electromagnetic fields that are interacting in heavy ion collisions. So let's go ahead and get started then. First, the Breit-Wheeler process, for those of you who aren't familiar, is a very simple QED process where two photons fuse into an electron-positron pair. So it's really one of the most simple QED processes for converting energy in the form of photons into matter and antimatter. And this process was theorized really at the beginning of the kind of the birth of quantum mechanics by these two physicists, Gregory Breit and John Wheeler. Their paper was published in 1934 in Physical Review Letters. And really what it is in Feynman diagram notation, it's quite simple. You have these two diagrams where the photons are interacting through a virtual electron-positron line to produce an electron-positron pair. There's two Feynman diagrams interacting at lowest order. And of course, this is an interaction which is forbidden in classical electromagnetism. But of course, in quantum mechanics, with the ability that the vacuum has to fluctuate into a pair, you have the ability for photons to interact. Now, this is something that's been sought after really pretty continuously since it was predicted 85 years ago. And it's been actually sought after at different times in different fields most fervently. Most recently, it's actually been a very important topic in laser physics. But we've also been interested in it in heavy ion physics at different times throughout the decades. What I want to talk to you about in this talk is really how we can use this process to address applications in nuclear physics, specifically high energy nuclear physics. So I think many of you are certainly well aware, but when we have these ultra relativistic heavy ion collisions, what we do is we produce highly Lorentz contracted electromagnetic fields. That's what this illustration shows on the left. So you have fields that are compressed almost entirely into the transverse plane. And the important thing is that you have an electromagnetic field, which emanates outward, and a magnetic field, which circles. And these are compressed to the point where at any given point, the field appears to be a linearly polarized electromagnetic wave. And this is important, and it can be understood through the Weizsäcker-Williams equivalent photon approximation, which essentially tells you that for a given field, how do you quantize that into photons? So it's a connection between the classical field and the quantum. The important thing is that in heavy ion collisions, we have a large enough charge that Z alpha is close enough to 1 that we can actually achieve these photon-photon interactions. And one way to think about that is that we have really strong electromagnetic field strengths. So in terms of the magnetic field, this is the strongest field that we know of in the known universe. And it has already been used to test QED in extreme conditions. For instance, the discovery of light by light scattering in heavy ion collisions by the ATLAS collaboration. So the question you may be asking is, what's new? We've been doing heavy ion collisions for at least 20 years, and these types of interactions were studied to some degree really since the beginning. And so just to give you a little context, STAR was the first one to look at photon-photon interactions in these ultra-peripheral heavy ion collisions where the nuclei don't actually interact. And back at that time, the statistics were quite low with only around 50 pairs. And there was comparison made to a couple of different models of these photon-photon interactions. Now, based on the information that was available at the time, the conclusion made sense, but it was unfortunately a bit incorrect. So in that paper, people found that the PT distribution of this electron-positron pair that's produced had a larger, on average, a larger value than what they expected if the photons were behaving as real photons. And so this was interpreted that because these electromagnetic fields are not perfectly contracted into the transverse plane, really the photons behave like virtual photons, and you have this kind of anomalous energy in the system which shows up as an extra PT. What I'll tell you is that this is not really correct, and that by learning through this experience, it's opened up a bunch of new applications. So one of the ways that this was addressed was through progress from a theoretical standpoint. I think there's been a lot of progress from theory and from experiment really pushing each other. So theory makes some progress, which pushes the experiment. Experiment makes some progress, which has pushed the theory. And really over the last 5 years, there's been a lot of interest in these processes. And so you can see that there's been development in a couple of different areas. So really rigorous calculations of this photon-photon process based on the Feynman diagram approach in lowest order QED. There's been applications to the Wigner function formalism, which is only applicable in the case that the photons are real. And there's also been recently some work to approach this from the classical field approximation. And actually this paper does a really good job of discussing the similarities and differences of all of these different approaches that people have taken recently. One of the things that all of these new approaches that are quite rigorous come to is that the interaction behaves as real photons, and I can talk more about why that is as we go through the talk, but the interaction really proceeds as real photons with linear polarization. And this is a new topic that we didn't understand previously. So we're sensitive to the polarization effects of the colliding photons. And the other thing is that the initial photon transverse momentum is actually determined by the electromagnetic field distribution. So it's these two ideas that I want to explore through the rest of the talk. So first, we'll talk about this idea of the photon's linear polarization, because this was really a new and unexpected effect. So the polarization of these two photons actually ends up producing a very important and essential signature of the Breit-Wheeler process. So if you look over here in the top left, this is now a view of these heavy ion collisions looking at the transverse plane. So you have the ions passing one another, and the electromagnetic fields, like I mentioned before, are arranged in such a way that at any given point, the photons interacting are linearly polarized. Their polarization vector is determined by the electric field line and is perpendicular to the magnetic field line. And so what you can see here is that depending on where in space these two photons interact, you're actually going to have different relative photon-photon polarization angles. Now, this is a concept that was actually, it was actually realized that this was important all the way back in 1952 by John Toll, but unfortunately he didn't publish these results. They were in his thesis, and I think some of it was forgotten for that reason. So the idea here is that we can actually use the polarization effect as a key signature of this process. And the idea is actually quite simple. If you have the generalized density matrix for this two photon system, these photons are spin 1 particles, so it's a 3x3 matrix. And in general, a spin 1 particle can take on plus, minus, or a 0 state. However, for real photons, we know that they can't take on this 0 state. And so what that does is it ends up making it so that you only have a few select parts of the wave function that can actually be interacting if the photons are behaving as real photons. And we looked for exactly the signature in STAR. And what we found is that when the photons interact in a mostly parallel way, you get this positive cosine 4 delta phi. And when they interact in a mostly perpendicular way, you get the opposite sign. It turns out that most of your interactions occur right here, where you get mostly parallel or anti-parallel polarization vectors. And so what you observe in the end is this cosine 4 delta phi modulation. And you can see the measurement in ultra-peripheral collisions on top and peripheral collisions on the bottom. In the red, you can see the fit to the data, and in the blue is actually the QED prediction. So you can see that in both cases, it agrees extremely well. And this was proof that we actually have access to this photon polarization for the first time. Now, because this is a key signature of the Breit-Wheeler process, this was the key element in the discovery of the Breit-Wheeler process, and it was picked up by quite some media outlets and has become a very highly cited paper just in the last year. I think we're at 67 citations. So like I said, that was the first key feature, was this polarization dependence, and I'll say more about that as we go through the rest of the talk. But the second important part of this is that the initial photon transverse momentum is determined by the EM field distribution. And so if we go back now, I showed you a few slides back this very early STAR measurement where you had this disagreement in one of the predictions and the actual measurement. Well, you fast forward 20 years and we have much more precise measurements. So this is the transverse momentum of this E plus E minus pair. And the problem is that traditional EPA calculations really predicted that the transverse momentum would be peaked at this very, very low value. And as you can see here, the data clearly shows a higher transverse momentum. Now, again, this was previously interpreted as kind of an anomalous excess in energy compared to the assumption of real photons that shows up as an additional transverse momentum. It turns out, though, that what's really happening, I've already given you the answer, is that the actual initial KT of the photons depends on their distance from the center of the nucleus. Really, it depends on the electromagnetic field distribution. And so the way that we can test this is by looking at interactions that occur at large impact parameters, where on average the photons travel a long distance, or looking at small impact parameters where the photons travel a much shorter distance. And here you can see the UPC result with the QED prediction. And then if we add in the QED prediction for the smaller impact parameters, the 60 to 80%, you see that it actually agrees quite well. So this is really the important and key aspect, is that we have sensitivity to the spatial distribution of the electromagnetic fields. And this dependence was actually recently confirmed by the CMS experiment. And so you can look at their paper as well. So here's the really important part of this, which is that because of this dependence on the spatial distribution of the electromagnetic fields, we actually now have a procedure for mapping the field strength in space through these processes. So it's relatively simple. The idea is that you measure this distribution. So this is the cross-section as a function of the pair PT. You compute the QED prediction for various electromagnetic field inputs, and you find all QED configurations that fall within the experimental uncertainties. Now, the important thing here is that because this is a pure QED process, there is essentially no theoretical uncertainty. The only free parameters, if you want to call it that, are the four potentials that you put in, which are governed by the form factor of the charge distribution. And then there are the kinematics of the photons, which is related to the form factor. And the idea here is that once you put this in, you can actually make these calculations and compare with the experiment. So to give you an idea of what this actually looks like, what I'm showing you here is the two photon overlap function. So the way that you can interpret this is that you have the fields of these two nuclei that are quantized as photons, and wherever this is bright, you have a high probability of two photons interacting. When you're at these large impact parameters, you actually have essentially an equal probability of interacting anywhere around either of the two nuclei. Now, if you think about the individual photons, what this means is that you have a photon which travels a short distance and has a high KT, and then you have a different photon which travels a longer distance and has a low KT. So overall, the pair inherits a smaller amount of transverse momentum. As you decrease the impact parameter, you end up having most of your interactions in a small region just between the two nuclei. And now what you end up with are two photons with relatively higher KT, and you have a much smaller region where you're producing the interactions. So the angles, like I said earlier, are constrained to this mostly anti-parallel case. So, like I said, you can take this information and run the QED calculations and look for the distribution of the fields that are consistent within the experimental uncertainties. And so you can do that by looking at the skin depth and the radius of a Wood-Saxon charge distribution. And then you can look at this contour, which tells you which distributions are consistent within 1 or 2 sigma of the experimental uncertainties. Now, unfortunately, there's a bit of a correlation between the skin depth and the radius, which basically just means that you're not sensitive to those really high frequency features, but you're sensitive to the overall size of the electromagnetic field distribution. So if you actually put this in space, spatial coordinates, you get something like what you would expect. You get a very strong field near the edge of the nucleus, which drops off pretty rapidly. In one dimension, it looks like something like this. One of the interesting things is that, as we would expect, the field strength inside the nucleus is not super well constrained at this point. And this is interesting because that's the part of the field which drives a lot of these effects, even like the chiromagnetic effect, especially as you get to more peripheral events where the field direction and the strength could vary a lot due to the exact fluctuations in the nuclear geometry. Now, to put this into perspective, we have very high precision charge distribution measurements from low energy electron scattering experiments. So if you look on this plot on the right, that's given by this purple cross. So we have these very precise measurements of the charge and skin depth. And if you put these contours that we extract at high energy on this same plot.
You have 5 minutes, okay?
Perfect. What you see is that while we're roughly consistent, we actually have tension on the order of about 3 sigma. And this is quite interesting because there's different possible reasons why you might expect the charge distribution to swell up as you go to very high energy. One of the things that we've been exploring is looking at the energy dependence of these highly Lorentz contracted fields. This is interesting because as you go to lower energies, the Lorentz contraction becomes less complete, and you actually get something like an infrared divergence of the field, which is only cut off by this omega over gamma factor. And so what that means is that the cross-section for the Breit-Wheeler process actually drops very quickly. And what you can see here on the bottom is that the way that the cross-section evolves actually becomes quite sensitive, again, to this form factor or the charge distribution. We've looked at this energy dependence. It's still preliminary, but we're working on a paper. And we're able to show, though we have large uncertainties, that indeed we see this fall off in cross-section that you would expect due to this infrared divergence of the fields. We were able to repeat the same procedure in our 54 GeV measurement. So this is a similar measurement of the skin depth and charge radius of the colliding charge distributions. What you might find here that's interesting is that the blue now is the 54 GeV, whereas the red is all of the 200 GeV data. The blue and the red barely overlap. The blue is actually consistent with low energy electron scattering. And so there's, I would say, just a hint at this point of some energy dependence of the charge distribution as we go from 54 GeV up to 200 GeV. We're actually eagerly awaiting some measurements like this from the LHC to see if we can observe a more strong dependence on the energy. So with that, I wanted to move to experimental constraints on the initial EM field for the isobar. So as I mentioned earlier, the isobars were extremely important for the CME measurement. Now, the possible null result opened up quite a few questions about our assumptions going in. Probably the most significant of these questions is how well do we actually know the initial EM fields? And so we can actually use this process to help answer that question. What you see here on the left is a measurement of this photon-photon to E plus E minus process. And at very low PT, you see this peak in the cross-section when the coherent EM fields are interacting. Now, because this is the process taking place in these hadronic interactions, we have to statistically remove the contribution from hadronic interactions, but we're still able to isolate this electromagnetically driven component. If we compare the production from the two different isobars, what we find is that in this very low PT region, where the process is driven by the coherent fields, we have a difference in cross-section, which is between ruthenium and zirconium, which scales as the Z to the 4th power, which is what we would expect if the electromagnetic fields are different by this about 10% as we expect. Now, this is only at about the 3 sigma level, but there's actually one other way that we can approach this. So instead of using a photon from each field, we can use a photon from one of the nuclei, which fluctuates into a quark-antiquark pair and interacts with the other nucleus. Now, when this photon interacts, the photon flux is given by the coherent field of one nucleus. So in this case, the cross-section is expected to scale as about z squared power. Again, we have relatively large uncertainties, but if you put this measurement and the previous measurement together, you have about a 3.5 sigma effect that shows that there is in fact a difference in the initial electromagnetic field between the two different isobars. And so this is exciting because it shows us that we do understand the fields, even though there are some differences that we can't constrain with the current uncertainties. Here's just another way to look at that and to understand this kind of map that we're building for nuclei at different Z. So you can see the isobars over here in red, and you can see gold and uranium. And again, this dotted line is the expectation if the field evolves the way that you expect. So the photon-photon interaction basically goes as Z to the fourth. So with that, I guess I'll end in the last just minute or two to talk about some of the exciting future opportunities. So I showed you this plot earlier where we've been able to measure these photon-photon interactions even in hadronic interacting collisions. Even though the result is consistent with just an initial state effect, we actually find some tension, and we expect that the data is actually best explained with about 15 MeV of additional broadening. Now this is interesting because if you have a long-lived QGP that traps the field and modifies this PT distribution, that's exactly what you would expect. Now that we have data at these lower energies, it's actually interesting because the field, the field is traveling through more slowly, and so you could, in principle, have a larger effect due to these lifetime effects. And at 54 GeV, again, we have relatively large uncertainties, but if you put everything together, we have a hint of this systematic increase above the QED baseline, which is roughly consistent with what you'd expect by a trapped electromagnetic field. Actually, we're really interested in people that might want to carry out more rigorous calculations of what a trapped electromagnetic field would do in this case. And then I'll just end with this, which is that in the next 2 or 3 years, STAR is actually going to collect 20 billion events, which will give us about 1,000 times more statistics for these types of measurements. And we're going to be collecting them in a way which is really perfect for UPC events. And to give you an idea of 2 of the different things that we hope to do, we're going to look at this polarization-driven effect, this cosine 4-phi modulation, and we're going to look at the PT distribution. When we look in the events that actually produce a quark-gluon plasma, along with these photon-photon interactions, what we find is that there's currently a little bit of tension, and with the added precision, we'll be able to see if there is in fact a disagreement with the QED baseline, which may be interpreted as a final state electromagnetic effect. So with that, I'll go ahead and end. I think the idea that I want to leave you with is that the discovery of the Breit-Wheeler process has opened up a whole bunch of new opportunities with photon-mediated processes. And specifically in the next 2 or 3 years at STAR, we're going to have the most significant increase in statistics that we've ever had. And it will allow us to really answer some of these questions in a very quantitative way. So with that, thank you.
Okay, thank you. Thank you, Daniel. Questions?
Hi, Daniel. It's a very nice presentation. Thank you. Very brief comment and then a question. A brief comment is that we calculated the dilepton production from plasma with a magnetic field, and it enhances a lot that production. And the question is this. When you're considering such strong magnetic fields present in between the ions, it seems natural to have the process of one photon going into a lepton pair which will be a high probability because it's not suppressed as much. Your process is alpha squared. That will be only alpha. For such strong magnetic fields, I believe it might be dominating. Any comments?
So I'm having a little hard time hearing you, but I think what you're asking about is a photon going into E plus E minus, right?
Exactly.
In the presence of the field?
Exactly.
Right. So this is where I think as we move into experiments that have different acceptance, I think we may be more sensitive to these types of opportunities, probably more so at the LHC with the future upgrades. I think the simple answer, as far as I understand, is that when we look just at mid-rapidity, as we're doing in this case, we're not terribly sensitive to the kinematics that you would expect for this type of process. If you go more forward or backward in the beam direction, I believe you should be able to see the excess that you're talking about. Unfortunately, I think it's just not possible with STAR in its current configuration.
Okay, thanks.
Okay, just one more quick question.
Thank you. Okay. So, thank you very much for a very nice talk. Actually, the UPC is extremely interesting. I read a couple of your review articles. That was really inspiring. And so my question is about the polarization. You mentioned that the photon polarization is quite important. That is quite interesting. And my question is, probably during the talk you mentioned, but it was too fast. So my question is, what is measured in the experiment is a dilepton. And then what is actually the effect of the polarization the polarized dilepton directly measured in the experiment. So if the photon is linearly polarized, I would expect some polarization in the dilepton itself.
I'm having a bit of a hard time hearing, but your question is related
let me repeat my question. Okay, the dileptons may be also polarized as an effect of the linearly polarized photon. And then the polarized dilepton could be directly measured in the experiment. And so what is the theory expectation?
Right. Okay, so, well, I think, so in this case, what's happening, I went through this a bit quickly. What's happening is you have the photons interact, and you essentially have 2 units of spin in the system. However, what the calculations show is that in general, the E plus E minus are produced in a singlet state. And so what you have is that the 2 units of spin actually get embedded into the orbital angular momentum of the E plus E minus. So that's what we're measuring, is that this cosine 4 delta phi it's essentially the spherical harmonic that you expect when this spin 2 composite state decays into the spin 1/2 daughters. I think in that case, the daughters themselves are not necessarily polarized. And even if they were, we don't have like a Stern-Gerlach type experiment to measure polarizations or spin directions in our experiments. Generally, in heavy ion collisions, we use special decays like the lambda hyperon, to look for cases like this where you have spin alignment. So I'm not sure of the potential to do that, at least with existing experiments. I hope that answered your question.
Okay, so you said that it is not necessarily polarized, but is there any theoretical computation to estimate the magnitude, or is there no theoretical estimate yet?
I think this may be, if I heard you correctly, more of a theoretical question. One of the things that people are working on is looking at all of this a bit more differentially. So for instance, this effect that I'm showing you here, it has some differential structure in PT and in rapidity. And this is where you'll become more sensitive to these details of the kinematics. The other thing that STAR is doing, which I think is a little bit of an answer to your question, is that we're looking at the difference between electrons and muons. So I wasn't able to show you any results of photon to muon today, but we're hoping to have these results relatively soon. And in this case, there's actually quite a few things like this that you can look at, because the difference in mass affects the ratio basically at which these interference effects happen and the kind of these polarization effects that you're talking about. So I think that's probably experimentally the best way to go about it, is by comparing production of E plus E minus to mu plus mu minus. And I can already tell you what we're looking for is that this distribution gets significantly modified by the mass of the muon, because you're more sensitive to some of these other effects. So I'd encourage you to look at our paper if you're interested. We do talk about this a little bit.
Okay, thank you very much. It is very interesting.
Okay, thanks, speaker,
Thank you.
again.